In the name of Almighty God, I am Master Hassan Kashi, and today I want to talk about electron beam divergence due to self potential. Electron beam divergence happens due to self potential, which is the repulsive electrostatic force electrons exert on each other as they travel in a beam. This inherent space charge effect causes the electrons to spread out, leading to divergence, which reduces beam quality and makes it harder to focus to a small spot. To understand this phenomenon fully, a self-consistent computation of particle trajectories and the electric field is required, as the self-consistent calculation shows how the particle perturb the field and how the perturbed field affects the particle motion. The mechanism of self-potential. The first concept is electrostatic repulsion. The fundamental cause is Coulomb's law, which dictates that like charges repel. Since all electrons in a beam are negatively charged, they exert a repulsive force on each other. The next concept is space charge. The collective effect of these repulsive forces is known as the space charge effect. As the electrons move together in a beam, they accumulate a net negative charge within a certain volume, creating a self-generated potential. The next concept is divergence. This repulsive force acts to push the outer electrons of the beam further away from the center and from each other, resulting in the beam's outward spreading or divergence. Factors influencing divergence. The first factor influencing divergence is electron energy. Higher longitude energy and longer acceleration lengths for the electrons can lead to a reduction in space charge effects and therefore less divergence. The next one is beam parameters. A higher beam current, which corresponds to a large number of electrons, increases the space charge and thus the divergence. The next is electron bunch duration. A shorter bunch duration also contributes to a stronger space charge effect, leading to greater divergence. The next one is beam quality. Higher divergence means a lower beam quality, making it more challenging to focus the beam to a very small spot. And what are modeling self-potential divergence? The first one is self-consistent calculations. To accurately predict divergence, it is necessary to compute particle trajectories and fields self-consistently. This involves an iterative process where particle trajectories are calculated, the space charge density is determined, and then these trajectories are used to calculate a more accurate electric field. COMSOL software simulation. Software like COMSOL can perform these self-consistent calculations using its particle tracing module, allowing for the analysis of strongly coupled particle field systems under steady state or time-dependent conditions. When modeling the propagation of charged particle beams at high currents, the space charge force generated by the beam significantly affects the trajectories of the charged particles. Perturbation to these trajectories in turn affect the space charge distribution. The charge-particle tracing interface can use an iterative procedure to efficiently compute the strongly coupled particle trajectories and electric field for systems operating under steady-state conditions. Such a procedure reduces the required number of model particles by several orders of magnitude compared to methods based on explicit modeling of Coulomb interaction between the beam particles. A mesh refinement study confirms that the solution agrees with the analytical expression for the shape of a non-relativistic paraxial beam envelope. The next concept is a fundamental investigation into the role of beam focal point and beam divergence on capillary stability and evolution in electron beam welding applications. In this simulation, a novel mathematical framework that fully describes fusion and vaporization state transitions in multi-component substrate has been applied to assist in understanding the fundamental mechanism of thermocapillary or keyhole formation and stability during the electron beam welding process, specifically the role of electron beam divergence and the location of the beam focal point within the substrate is numerically investigated. It is shown that the location of the beam focal point directly influences the keyhole formation dynamics and leads to drastically different keyhole structures. It is further shown that a less divergent electron beam has a greater penetration rate and procedures a more stable thermocapillary. The next one is fabricating. Fabricating metallic joints through electron beams or EB welding or other higher energy density processes such as laser or plasma arc welding presents an exciting opportunity to reduce fabrication costs when compared with traditional arc jointing technologies. The cost reductions offered by EB welding are particularly attractive during the fabrication of safety-critical primary circuit components for nuclear power generation, where the adoption of higher energy density fabrication technologies offer a step change in the planet construction economics. During EB welding, a focused beam of electrons is directed at towards the surface of metallic substrate in a vacuum. The electrons in the beam transfer their kinetic energy to thermal energy upon interacting with the substrate. With sufficient power density, a thermocapillary or keyhole is generated through the substrate as the material is vaporized, allowing the beam of electrons to penetrate further into the substrate. This thermocapillary generation is the mechanism by which this process has such high productivity as very thick sections may be joined in a single application of the beam. However, the high-velocity nature of fluid and vapor flow within the thermocapillary means that this structure can be a source of significant porosity in the finished joint, as vapor bubbles can be entrained within the solidifying material. Mathematical modeling of EB welding presents a unique opportunity to understand the fundamental physics responsible for the compositional, topological, microstructural, and thermomechanical changes that happen during the process. In fact, the highly transient nature of the flows in EV welding and materials joint mean that it is often impossible to accurately observe the flow phenomena experimentally. Mathematical models are also useful in obtaining accurate descriptions of the fabricated joints as the components enter into service, permitting the faithful prediction of safe operating limits and lifetime evolution of the joint region. These mathematical descriptions of the joining process also offer the opportunity to optimize the processes through simulation at a fraction of the cost of an experimental campaign, or to at least narrow the range of parameters investigated experimentally. Traditional weld modeling approaches neglect the fluid dynamics of the molten and vaporized region entirely, instead using phenomenological heat source descriptions to represent the complex physics involved in the fluid region and obtain thermal predictions by solving a simple heat conduction problem either numerically or analytically. These thermal fields are then typically used as the input for a residual stress computation. For predictions of microstructural evolution, phase field frameworks are preferred for their ability to incorporate a variety of interfacial physics and bulk kinetics to predict the resultant polycrystalline structure. For predictions of the topological evolution, including the fluid flow and macroscale solidification behavior, thermal fluid dynamics frameworks are used that describe the momentum, mass, and energy conservation within the domain. Recently, this thermal fluid dynamics approach has been extended to multi-component substrates with an explicit treatment of the vaporization state transition per chemical species, permitting high fidelity simulation of the fusion and vaporization state transitions in alloys without the need to fit phenomenological recoil functions as is done elsewhere. In this work we will use this recently developed high-fidelity multi-component framework to numerically investigate the effect of electron beam divergence and focal position on the evolution and stability of capillaries formed during electron beam welding of 5 mm thick SA 508 ferritic steel substrate. In addition to relating the keyhole formation dynamics to the electron beam characteristics in terms of beam divergence and focal plane location, the high-fidelity numerical framework permits predictions of perfectional element evaporation from substrate during these processes. It will be shown that the framework predicts significant losses of the higher alloying element components in the substrate, namely Mn or Cr, while the heavier elements with greater vaporization temperatures are not as significantly perturbed. And what is the method? To mathematically describe the multi-component system experiencing fusion and vaporization state transition, a framework of partial differential equations is used to describe the conservation of momentum, the conservation of energy, and the conservation of mass. A description of the framework used in this work can be found elsewhere. In this simulation, the description of the heat source has been extended to account for the diverging and oscillating nature of electron beams. The highlights of the mathematical frameworks will now be briefly presented, as well as a description of the spatially varying Gaussian heat flux. And what are our conclusions? In this simulation, we show that during the electron beam welding of a multi-component metallic substrate, the focal point of the beam and beam divergence govern the formation and stability of thermocapillaries. It is shown that changing the focal position from being located at the top surface of the substrate to being located mid-depths or located at the bottom surface, a full penetration thermocapillary can be generated instead of a partial penetration thermocapillary, demonstrating that under-focusing of the beam is a crucial component for successful EB welding procedure development. Furthermore, it is shown that decreasing the beam divergence leads to a higher propensity to generate greater penetration keyholes. Also, during the transition from partial to full penetration through decreasing of the divergence, it is shown that some instabilities indeed form at intermediate beam divergences, while the compositional changes in the substrate due to preferential element evaporation during the electron beam welding process are not the primary focus of this simulation. It is also predicted that in the SA 508 substrate considered, we expect to see significant Mn loss. This will be explored further in the future. Specific summarized conclusions to this simulation are as follows. The first one is the location of the beam focal point determines the penetration rate and total penetration for beam power densities that are not sufficient to always fully penetrate the substrate. The next one is that as the focal point is moved to be at the bottom or far face of the substrate, larger thermocapillaries are generated and more material ablation is observed. The third one is as the beam divergence is decreased, full penetration keyholes are more likely to form. However, in the transition from partial to full penetration, these keyholes are more likely to be unstable. The fourth one is significant Mn and to a lesser extent CR evaporation is predicted for the electron beam welding of SA508 ferritic steel. And now you can see that I have used the charge particle tracing and electrostatic and here for multiphysics there is electric particle field interaction between these two, and you can see electric potential, electric field based on here that you can see volt per meter, and particle trajectories based meter. Thank you so much for watching my video until the end, and you can also download this computer simulation as electron beam divergence from my GitHub address /mahsa screen.